Hello, in this video we are going to just check our previous knowledge, and we'll also see a few new terms like current density. We'll derive Ohm's law, we will check what is conductivity and resistivity. So let's first check what we did yesterday. We learned about, okay, let me just select a pen, yeah. We learned about current and drift speed. In particular, we learned about drift speed. So drift speed is the speed at which the carriers move. That's what we learned yesterday. Yeah. We also derived this equation which relates the average current to drift speed. We defined what is N, if you remember. N is the number of charge carriers per unit volume. So in order to get the total charge which is passing through a cross-sectional area, we have to multiply with Q as well, which is a single charge carrier. This we did yesterday. The net drift speed, as I explained yesterday, is very small. Yeah. So basically, when there is no potential difference, the electrons are moving in random direction. But as soon as you apply a potential difference, that means you have applied an electric field. So the electrons start moving opposite to the direction of electric field because they are negatively charged, and they slowly start drifting. As in this case, you can see electric field is towards the left and the electrons are drifting towards the right. Now, you need to know that electrons are already present in the wire. Okay, they just respond to the electric field. That means whether you're applying potential difference or not, and which way is the battery connected will decide the direction of flow of electron. So battery is not supplying electrons, it is just establishing electric field, or in other words we can say it's providing energy to the electrons. Now this is a typical example to understand that drift speed is really very small. That means it's a very low, it's a very small value. So here you are having a drift speed for a 12 gauge copper wire. So it's a conductor, okay, which is carrying a current of 10 ampere, which is quite big current. So in that conductor, the drift speed of the electrons, which are the charge carriers, is to the power of 10 to the power minus 4. So you can see that that's the order of magnitude, and which is quite small. Now this is a quick quiz which is based on the charge carriers. So you can take a minute, you can pause the video and try to answer by yourself. It's asking to rank the current in these 4 regions from highest to lowest. Okay. So how do we rank the current? So current is based upon the magnitude of current is based upon the number of charge carriers, that because it is charge per unit time. That's how we define current. So more the charge, more will be the current. Now if you see here, and current, the conventional direction of current is in the direction of positive charge. Yeah. So if you are having a negative charge, the direction of current will be opposite to the direction of negative charge. So if you look at the first diagram, you have got 3 charges which are positive and they are moving towards right. And that means towards right, if I take each charge representing a unit current, so 3 units of current is towards right. Okay, and negative current is towards left. So that means effectively this negative current, this negative charge, when it moves towards the left, there is a current because of this negative charge towards the right. Because what is current? Current flows opposite to the direction of flow of negative charge. That's a conventional direction. That's how we define the conventional direction of current. So we have 2 negative charges which are moving towards which direction? They are moving towards the left. That means these negative charges are going to give current towards right. So we have got 2 negative. So because of these 2 negative, we have got current flowing towards right, and we have 3 positive, and all of them are moving towards right. So you will be having all the current which is flowing because of these charges, all of them are towards the right. So we are having how many units? 1, 2, 3, 4, 5 units. So we are having 5 units for the first diagram. If you look at the second one, we are having 4 units. The same principle you can apply for the for part C. We are having 2 positive towards right, that is 2 units, and 2 negative towards left, that also gives you 2 units of current towards right. So that's also 4. Yeah, this is also giving you 4 units. So just check that once again. We are having 2 positive charges which are towards right. So positive, positive, it's giving towards right, and 2 negative which is moving to left, but the current is towards right. So the current direction, the current produced is towards right. This is positive charge. So you have got a 4 units current flowing in C, 4 units current flowing in B. That means the magnitude for both of them is same, and you have got 2 units of current for D. Yeah, so you can then rank them accordingly. Let's now define current density. Yeah, current density is defined as current per unit area, which is current density is represented by the letter J, and because we said it is current per unit area, so I divided by A. Now the unit for current density is quite simple. We can get it from the formula itself, which is current is ampere, area is meter square. Don't get confused between this A and this A. This we are talking about units. Okay, here A is representing ampere, this A is ampere, whereas this A is area. Again, current density is in the direction of positive charge carriers. Now we are going to derive Ohm's law. Yeah, so we are going to look at these steps one by one. For some materials, the current density which we defined is directly proportional to the field, which is E, electric field. So you can see that in this equation we have J, which is directly proportional to E. Now this sigma which you see is a constant of proportionality, and we call it as conductivity. Now we are trying to get from here, from this step, we want Ohm's law, which is this step. So let's see how to do that. We are going to consider a conductor as shown in this diagram. You can see that the length of the conductor is L. It is having a potential difference, therefore there is an electric field which is E. So we can relate delta V, which is potential difference across the conductor, as EL, because we know delta V is ED. Recall that from our previous formulas. So here it is delta V is equal to EL, because L is the distance between the two faces of the conductor. So we put this E, we can get E from here. This equation gives you E, which is delta V over L. Okay, let me write it once again. E is equal to delta V over L, and that we replace back into the formula for current density. We rearrange the formula. You can see that we have rearranged. Okay, and then what are we doing? After rearranging, we are going to replace this J with its definition. So delta V is equal to L over rho. What was J? It is current per unit area. Okay, so so you can see that this I, we are going to keep it on one's like separate. So we can write delta V is equal to L sigma A, and we can keep I separate, yeah, inside. Now this del L is constant for a given conductor, sigma is a constant we defined as constant, A is constant. So that means this whole thing which you see here in the brackets, this is a constant, and we replace that by R, So our equation becomes delta V is equal to Ri. This R is called as resistance. Okay, so just now we can see we started from the definition of current density and we reached to the formula of resistance, and basically we defined Ohm's law. So the conductors which follow Ohm's law, they are called as ohmic conductor. The conductors which do not follow Ohm's law, they are called as non-ohmic conductor. So I want you to draw or sketch in your notebook the graph, IV graph. So what do you mean by IV graph? I on the y-axis and V on the x-axis, and sketch a graph for ohmic and non-ohmic conductor. Okay, it will give you a clear idea how the graphs differ and how the resistance is different for them. Now, if we go back to a previous slide, what did we get R as? So here we can just write R is equal to L sigma A. Yeah, this from here, from these two equations, we can combine and we can write R is equal to L over sigma A. So that's, I'm going to write here the same formula, R is equal to L sigma A. This is what we got, where sigma was conductivity. This sigma we can convert to resistivity. This is resistivity, which is rho, which we know from before. Yeah. So sigma we can convert to resistivity, and we can rewrite the formula as R is equal to rho L over A. So this gives you clear idea how R is going to change. Resistance is going to change. It is directly proportional to length, and it is inversely proportional to area of cross section. So remember, these two are quite important because it will be tested in different ways in multiple choice as well as in free response. Now let's just quickly check. You may pause the video and solve by yourself. Here it says a cylindrical wire has radius R and length L. If both R and L are doubled, what happens to resistance? So the first step should be to write the formula. In the formula we have area and we don't have R, so we have to bring R. So we'll write rho L over pi R square. Why pi R square? Because wire, yes, for wire the cross-sectional area is a circle, and for circle the area is pi R square. So now they say that double L as well as double the radius. That means radius is going to have more effect. If radius is increasing, that means resistance has to decrease. So our answer would be D. Next one, you have got an IV graph and is asking, and it's an IV graph for diode, is asking what is happening to the resistance. Now here I am going to give you a hint. You will get the answer by yourself and complete it in your notebook as homework. Now when you look at a graph, you need to get resistance from this graph. Yes, so if you see the graph, if you look at the slope of the graph, it's becoming steeper. Yeah, before it was less steeper. If I draw a tangent, I can see that the graph is becoming steeper. What does that imply? What do you mean by steeper slope? Can you relate this to resistance? Think about it and try to answer. Yeah, or you can also keep the formula in your mind. R is delta V over I. So check what's happening as delta V is increasing. Is I also increasing by the same amount or not? Now let's look at this example, which is from your textbook. You can again pause the video and read the question before we solve. We are having a coaxial cable. It is extensively used for cable television. Coaxial means same axis. They share the axis. Like in this case, you are having two circular cylinders. If you look at this diagram, There's a cylinder outside, there's a cylinder inside. They have the same axis which is going to pass through the center. That's why coaxial. Okay, in between the cylinder there is polythene, which we know is an insulator. Now here it's telling you, it's giving you the radius A as well as it's giving you the radius B and the length L of this wire, of this cable, and we are interested in the plastic which is in between the cylinder. The resistivity of the plastic is given to you. It's asking you calculate the resistance. Okay. Now this is interesting because we don't have a complete wire made of plastic. We have kind of a ring, okay, kind of a hollow cylinder of plastic. You can see that only this part, this green part, is made up of plastic. So if you look at the diagram carefully, this diagram, you look at the diagram carefully, we are going to consider a small section of this plastic, which we are labeling as dr. We are going to find the resistance for this, and then we are going to integrate it from inside to outside. Inside radius was A, outside radius is B. So let's see how to do it. So the first step is we are going to write dr. Remember the formula for R? This was the formula, you remember that, rho L over A. So because it's a small resistance, we are writing dr, rho is as it is. The length is dr because this is the length of the wire. We are trying to integrate this way. So this is the length of the wire, so that is dr. The area is the area of this circle which you see here, which is 2 pi RL. Okay, so we have got an expression and we are going to integrate it because this is only for a small element dr and we have to integrate it from A to B. Yeah, so as usual we put the integral, we take the constants out, we put the limits. We do the integral, we substitute the limits and we get this expression B minus A. So B over A, because it will be upper limit over lower limit. We substitute the values and we get the answer. Now that's it for today's class, and don't forget to complete the homework which is there on Google Doc. Okay, see you tomorrow.